Good morning, students. Can you hear me?
Sir, good morning, sir.
Yes, sir.
Yeah, thank you. So in the last class, we discussed about correlation, autocorrelation especially. So did any one of you trying to extract the pitch of your voice? Yes, did anybody try? So you can do wonders if you want to. Otherwise, so you're spending your time in a very unproductive way. So the choice is yours. Anyway, you know economics. So now we'll see the frequency response. What is frequency response? So frequency response is nothing but the response of the system for different input frequencies. So basically this is what you do. So you vary the input frequencies, and input frequency is for a signal, and signal will be having an amplitude. So input signal x of t you will have, and the amplitude will be, so input amplitude will be a. Then you find out the output amplitude, that is a naught, here it is ai. Then you find out the value of output by input amplitude, that is signal, the amplitude of the output signal by the amplitude of the input signal. Amplitude of the input signal is kept constant, so you will calculate this. So this will give you the gain factor. So then you plot this for convenience. You will plot this 20 log to base 10 of g. You will plot. Now you will consider these two parameters, that is the frequency versus this column. Then you'll plot this curve. So your x-axis is frequency and y-axis is this 20 log of gain. So you will get some curve. So you would have done multiple filter experiments or amplifier experiments. Okay. So in that amplifier experiments, you would have got various curves. The shapes of the curves would have been different. So if it is, you would have got something like this. So it is in dB, so decibels. You might have got curves like this. This is one kind of a filter response. You might have got a response like this. In this form you would have got, depending on what is your response, or you would have got some response like this. Okay, you would have got some response like this. Whatever. All these shapes depend on the design. So you would have designed a system. So in your case, it might have been a amplifiers or filters or anything like that. So you'd have designed different systems. So you have to study the response, frequency response characteristics. You would have designed a system and you would have plotted or analyzed the frequency response characteristics. Like this. So based on the shape of the curve, you can call them as appropriately. So you can call something as a low pass filter, and you can call this as high pass filter. It is passing high frequencies. Maybe you can call this as band pass filter and so on. Band reject filter, multi-band pass filter and so on. So this is what is frequency response. Now we will try to analyze the same thing in MATLAB. Okay, so you will be given a different system. You would have been given a system. Now you have to plot the frequency response. Now what is this? Given a system. So what is the meaning of this? A system means what? It can be in the form of a difference equation. Now we will limit our discussion to discrete time system. So it can be in the form of a difference equation. or it can be in the form of a impulse response, or it can be in the form of system response. Okay, so impulse response representation is h of n. System response is nothing but Z transform of h of n. So it may be this. So if a system response is given, then that will be in the form of a rational form, that is numerator function divided by the denominator. So difference equations can be of various forms, like some examples. So an example is y of n is equal to x of n plus x of n minus 1 is a one example of a difference equation. Though the coefficients may change, the number of terms, that is output terms and input terms, may vary. The coefficients may vary. What can vary is the coefficients can vary. Okay, and the number of terms can vary. So variables are the coefficient values can change and the number of terms, that is input terms and output terms, may vary. So one example is here is there is one output term, two input terms. So another example can be something like we have y of n is equal to x of n plus half y of n minus 1. Now here we have two output terms, but only one input term. So now the coefficients change. So this is how you may have different configurations. So these are all the systems. Okay. Now you have to study the frequency response of the system if it is given in any form like this. Okay. How do you study? So now we will take one example. So let us say you are given a linear time invariant system which is defined by equation, that is difference equation, that is y of n equal to half x of n plus half x of n minus 1. So let us say you are given this. Now you have to determine the frequency response of the system. So now we know the frequency response means we have to get a curve or a waveform like this. So in discrete terms, it is something like this. So your x-axis is frequency, that is w omega, and y-axis is h of e power j omega is a y-axis term. But frequency response is made up of two things, that is magnitude response and phase response. Okay, so the frequency response comprises of magnitude and phase response. We have to get these two curves. Okay, now how do we do that? So first we will see in theoretically what is the frequency response of this system. So how do we get the frequency response? So we have to get h of e power j omega. So we can get h of e power j omega by taking the dTft. So which is difficult directly from this difference equation. So what we will do is we will take the Z transform of this equation. So y of n Z transform is y of z. X of n Z transform is x of z, and x of n minus 1 Z transform is z inverse x of z. The coefficients will remain same. Next, once you have this Z transform equation, then you can simplify so that you can get the result in the form of y of z by x of z, which is same as the system response h of z. So this is nothing but 1 plus z inverse by 2. Okay. So simplify this and we'll get h of z is z plus 1 by 2z. Okay. How do we get this is, so we can simplify this as 1 plus 1 by z by 2. That's equal to z plus 1 by z divided by 2 will become 2z. So this is what we have got. This is what we have got. Next, the frequency response is nothing but from h of z, if you replace z is equal to e power j omega, we'll get h of e power j omega. This is nothing but the frequency response. So that's what we are doing here. So h of e power j omega is obtained by replacing z equal to e power j omega. So in that we have h of z is z plus 1 by 2z. So z is replaced by e power j omega. So plus 1 divided by 2 e power j omega. Right? Now we can simplify this like this. E power j omega plus 1 can be written as, you take e power j omega by 2, half of that common, and other half will be remaining. E power j omega by 2 will be remaining. Here it will be deficient, therefore e power minus j omega by 2 will be remaining, divided by 2 e power j omega. 2 e power j omega as it is. But we know that e power j theta plus e power minus j theta by 2 is nothing but cos theta. So here theta is omega by 2. So this will become cos omega by 2. Now other things, this element e power j omega by 2 by e power j omega will become e power minus j omega by 2. Okay. So finally we have h of e power j omega is e power minus j omega by 2 into cos omega by 2. So now this is the frequency response. But we want to plot it when we say that we have to get the two components of frequency response, that is magnitude response and the phase response. So magnitude response is nothing but take magnitude of this on both the sides. So we will be having h of e power j omega magnitude is nothing but magnitude of the right hand side component of this equation. That is magnitude of e power minus j omega by 2 cos omega by 2. But e power minus j omega by 2 magnitude will be 1, therefore that will be redundant actually, and you will be left with magnitude response is nothing but magnitude of cos omega by 2. So we will plot this. So the variable is omega. So on a axis, the x-axis we have a variable omega, and y-axis is the magnitude response. So this is the magnitude response. Now, how do we plot it basically? So we can plot this curve or this equation we can plot by changing this variable. So this is w is a variable. So variable, and for each value of w we can compute the magnitude here. How do we do that? So we can, just for reference here, we have written this table. So vary w. So w can go from 0 to pi unique values. that is 0 to pi. I have taken 4 or 5 values here. 0, pi by 2, pi 3, pi by 4 and 3 times pi by 4. Now, h of e power j omega is cos omega by 2. So that is cos omega by 2. Now, when omega is 0, cos 0 by 2 is cos 0, that is 1. Magnitude of cos omega by 2 will be 1 only. Then convert this into decibels. 20 log of this value will be 20 log of 1 is 20 into 0 is 0. 0 dB. So this is in dB. Similarly, we can fill up other values. When omega equal to pi by 4. So we calculated this value. When omega equal to 0, we got 1. In decibel values, when omega equal to 0, its value is 0. Similarly, when omega equal to pi, when omega equal to pi, cos omega by 2 will be cos pi by 2. Cos pi by 2, that is 0. Cos 90 is 0. Now magnitude of 0 will be 0 only, and 20 log of 0 will be minus infinity. So magnitude response will plot. So at omega equal to pi, the magnitude response will be 0. Okay, at omega equal to pi, magnitude response is 0. But on a decibel scale, at omega equal to pi, magnitude response is minus infinity. Okay, 20 log of 0 will be minus infinity. So in between, we can fill up the values like this. So when pi by 4 at omega equal to pi by 4, this value, cos of omega by 2 we have to compute. So cos pi by 4 by 2 will be what? We can just calculate that. We can make use of a calculator or a computer. So cos pi by 4 by 2 is cos pi by 8. I have typed this in MATLAB and I got 0.9239. So the value is so this is 0.9239. I'll sketch that here. So when omega equal to pi by 4, now this is 0.9239. But on a decibel scale, we have to take 20 log of 0.9239. So that will calculate in MATLAB. So 20 log of 0.9239 is around 0.6875. So we'll just directly take what is 20 log of cos pi by 8. We can take it directly. So that is minus 0.6877. So the magnitude value will be minus . Yes, we got the magnitude value will be minus 0.6877. So that we'll plot it here. So at pi by 4, we get in the decibel scale, it is minus 0.6877. We have plotted the same thing. Like this, we complete all the values, we'll plot them, and we get the two curves, that is the normal curve and the absolute curve and the decibel curve. Okay, so now you can see that it is behaving like in a peculiar manner. That means for higher frequencies, the magnitude, the response to the higher frequency is 0, is very less. Whereas the response to the lower frequency is high, means it is allowing low frequencies, whereas it is attenuating high frequencies. That is the observation. This is very easy to observe from this graph. Okay, now how do we perform an experiment in MATLAB? It is straightforward. The algorithm looks like this. What we have to do is, so we have the h of z. In this case, it is z plus 1 by 2z. The coefficients we have to feed in. So give the numerator coefficients of the given transfer function. The transfer function is obtained here. If it is not given, we have to derive it, and we will be getting the coefficients, numerator and denominator coefficients. So give the numerator coefficient. Numerator coefficients, these correspond to, this numerator corresponds to input terms, and denominator coefficients correspond to the output terms. Okay, so we will give the numerator coefficients and denominator coefficients. Then we will pass these numerator and denominator coefficients to a built-in function called as freq_z. Freq_z is a built-in function, okay, and to find the frequency response. We get frequency response, but we want magnitude and phase response. So the magnitude and phase response will be plotted using again the built-in functions like the ABS and angle commands, ABS command and angle command. So using that, we'll plot both of them, and that is what we are expected to get. So we are expected to get something like this. So we will get a decibel scale representation. So we are expected to get this curve. This curve we have to get. Now, when we perform that is, we have to enter freq_z. The numerator coefficients are this 1 and 1. Numerator coefficients are 1 and 1, and denominator coefficients are 2 and 0. So when we pass these two, then we get a output looking like this. The first term, this is called magnitude response, and the second curve is the phase response as per the with respect to the frequency. So whatever we had told omega, with respect to omega, we will get a frequency. But omega, as I told, it can go up to pi maximum, but here we are representing pi as 1, and it is normalized here. We can say multiple into pi radians per sample. So 1 corresponds to pi, 0.5 corresponds to pi by 2. Here 0.2 corresponds to 0.2 pi. So you have to multiply this x-axis with pi for visualization. So this is what we have to get. Now you see here, what we have got and what we have practically been able to achieve. You can see here, at this point when omega equal to 0, we the curve, the magnitude response looks like this, a lower slope curve, and here you can see that it's a lower slope curve, but it's a bit looking different because our scale is not proper. It's not logarithmic in nature. That's the idea. But at pi by 4, the amplitude should have been minus 0.6877 dB. Now, on this particular graph, you go to 0.25 position and you can see it is minus 0.6877 dB. Whereas at omega equal to pi by 2, it is minus 3 point some dB. Okay, it's like 0.7071, 20 log of 0.7071. If you consider, it will be minus 3.064 dB or minus 3 dB. Okay, so what we are able to get manually, that is by theoretical calculations, whatever we have got, it is exactly verified in MATLAB. Okay, in MATLAB, we get directly the frequency response in terms of magnitude and phase response. What is the phase response here? So h of e power j omega is e power minus j omega by 2 into cos omega by 2. The phase response, we can compute it here. The phase response is nothing but the angle of the frequency response is nothing but the angle of e power minus j omega by 2 cos omega by 2. We know cos omega by 2 doesn't have any angle, but it is only e power minus j omega by 2 is what is, cos omega by 2 is the magnitude, whereas e power minus j omega by 2, e power minus j omega by 2 will have the angle. So angle of this is nothing but, see, e power j theta, angle is theta. So here the angle of e power minus j omega by 2 is minus omega by 2. Okay, so at whatever frequency you are trying to analyze, the phase response is negative of half the frequency at that point. That's all. So we can write the phase response directly like this. See, the h of e power j omega, the angle at 0 is minus omega by 2. Minus 0 by 2 will be 0. And here it is minus omega by 2 is equal to minus pi by 8. Here it is minus pi by 2 by 2, that is minus pi by 4, and so on. Here it is pi, therefore the answer will be minus pi by 2, and so on. So if you plot that phase response, it looks like this. So h of e power j omega angle is nothing but, so this is omega, omega equal to 0, pi, pi by 2, and this is pi. So at 0 it will be 0, so we can put the curve directly 0. At pi by 2 it will become minus pi by 4. So this is This is minus pi by 2. So at pi, it will become minus pi by 2. At pi by 4, it will be minus pi by 4, and so on. So we can write the curve in this manner. This is the phase response. Phase response. Okay. That's exactly what we are getting here. The magnitude response we verified. Theoretical calculation and MATLAB output. Whereas theoretical calculation of phase response is at 0 we get 0. Yes, that is verified. At pi we should get pi by 2. So pi is 180, pi by 2 is 90. So at this point it is around minus 90. So at pi by 2 it should be pi by 4. So at pi by 4 means 45 degrees. So this is in degrees, therefore it is 45 degrees. So that is also verified. So the frequency response of the system, which is defined using a linear time invariant difference equation, we have plotted it. Okay, the code for the same looks like this. It is very simple. So initial clear, close all, and these things. Then you have to enter the numerator coefficients of the transfer function, or they can be the input terms. Then you have to enter those values in an array through a square bracket. Similarly, you can enter these coefficients of the denominator of the transfer function into a variable a. Then we will use this freq command of this numerator coefficients and denominator coefficients. These two together forms the transfer function, and we will collect the magnitudes and frequencies into h and w. Okay, h represents the magnitude, that is the amplitudes of the frequency response curve, but this will have the magnitude and phase. Okay, therefore what we have to do is we have to plot now. Plot with respect to the frequencies w's. 20 log of absolute value of h will give you the magnitude, whereas in the second plot we can plot angle of h, that gives the phase of this particular h. So this is what we got after using the set code here. Okay, so magnitude response we have got, phase response we have got. Okay, we will test it. We will test one thing. So we will test it. So testing is basically it is mainly for your understanding. I am showing. Otherwise, plotting up to this point is sufficient. Okay. So give input. Filter the signal, filter the input, and plot the input and output waveforms. This is the template that we are going to try. So what we'll do is, see, as per this, what it says, if you give a DC signal, DC will be not attenuated. It will be with 0 dB. That is, it's not attenuated. Whereas when you give high frequency, like very pi by pi frequency, then that component will be attenuated. Therefore, what we will do, we will give an input like this. Let that input signal be in this form. It is made up of a DC component plus a high frequency component. That is, let this be cos omega n. So omega 1 n. So let omega 1 equal to 0 and let omega 2 will be pi. High frequency will take high frequency plus cos omega 2 n. So let us define n. N is number of samples, 0 up to 100 samples will take. Okay. So we'll take this. Now x. So x in MATLAB we cannot specify like this. Okay. So now output we have to get. So output is nothing but filter. We have this command. This you have used filter. The system we have to give in the terms of numerator and denominator coefficient. That is the input coefficients and output coefficients and the input that you have specified. Okay, so now you have the input, you have the output. So you can plot these curves in a same figure. That is input you can plot and you can plot the output and you can compare. So we'll do this particular part now. So testing the implementation. So what is that we have to specify? So numerator coefficients will directly specify here or will generate the signal, generate the input signal. So time you will specify that is a sample instant 0 to 100 samples and the frequency. So W1 is 0 and W2 omega 2 is pi. Two components we have seen. X is equal to cos omega 1 n plus cos omega 2 n. Okay, so this is, we can call this as high frequency component and this is low frequency component. Then we will add up these two and make it low frequency component plus high frequency component, so that when we separate this, it is easy for us to plot it. Okay, so now we will get the output. So filter the input through the system. Output is nothing but filter the numerator coefficients that is B and the denominator coefficients and the input. So you got this. Now you can plot the response, the waveforms. So first input signal will plot, subplot. So 2 rows one column first figure, then you stem with respect to n the input signal, and similarly the second signal is your output signal. Here it is output, this is input. So we'll just plot this for the same coefficients. So numerator coefficients x of 1 and 1, and denominator coefficients are 2 and 0. How? So the numerator coefficients are 1, the coefficient of z is 1 and the constant is 1. Therefore 1 and 1 are the numerator coefficients. Denominator coefficients are z coefficient is 2 and constant coefficient is 0. There is no constant here, therefore it is 0. That's how we have fed the data. Now you can see here. Now I'll just copy, I'll paste it here for analysis. Okay. Now you can see here the input. This is the input, and input is going something like positive. If I try to plot this, it will be like this: positive, negative, positive. I mean, this is very difficult. What I'll do is I'll just limit this. Okay. I'll set the axis. Let it go from 0 to 10. Minus 1 plus 3. Okay, I set the axis. I'll copy this figure. Copy. Okay. Here we'll try to draw. So how is our input? Our input is above DC. So this is the 0 line. Okay, 0 line. Now all the samples are either 0 or above 0. If you take the average of this, it is a 1. 1 is our average. So this is the average. But the signal is varying like this. So it is going from positive to negative to positive to negative, positive to negative, and so on. Okay. So it's a cosine wave. Okay. So it is a cos wave starting from the high value and going up to 0 value. So it's a cosine, and it's a cosine shifted upwards, therefore it is having a DC. So this is the DC value. But after filtering, what is happening you see here? It is only having all the samples are of amplitude 1. That is, the average is 1. Average of all the samples is 1, and each of the sample is also equal to 1. Therefore, it is a DC line. So if you can combine this and plot it, it looks like this. It's a DC step kind of an output. It is allowing only the DC. Where did that variation go? That is, where did this variation go? That variation has been suppressed. the variation is suppressed, whereas the constant or average is retained. Okay, so this is the meaning of this. By what value this variation is suppressed? This is multiplied by a 0, whereas the constant value is multiplied by 1. So multiplication factor, where is that we see this? It is seen from this curve. Okay, so the DC value multiplication factor is 1, whereas the high frequency multiplication factor is 0. Similarly, we can experiment by allowing a higher frequencies terms. Okay, now what you can experiment is you can change the transfer function. That is, you consider a different difference equation. We had considered half x of n plus half x of n minus 1. You consider half x of n minus half x of n minus 1. So what is that you are going to get? Your transfer function is going to be different. So it looks like this. So now you have got as a low pass filter. Later you are going to get for this, you are going to get as a high pass filter like this. So for this you may get different filter. For this you may get a different thing. So here, so some system is given directly in the terms of Z transform. So directly numerator coefficients are 1 and 1, denominator coefficients are 1 and minus 0.7071. So like this we can test our implementation. So this is about frequency response of a system given the difference equation. Frequency response of a system given the difference equation or a system response. Okay, so this is about the lab. So if you have any questions, you can ask me. Any questions?
So filtering the input means, are we removing the higher frequency terms?
See, for this particular example, what is that? It is acting like what kind of a filter? See, in this example, the frequency response is like this, correct? What kind of filter it is acting like?
Low pass.
Low pass filter. Low pass filter means what frequencies it will allow?
Lower frequency.
Lower frequencies. Higher frequencies it has to suppress. Now, in the example, what are the two frequencies that we have considered?
Low and pi.
Low frequency is DC, that is 0. High frequency is pi. So this is a low frequency and this is a high frequency. So which is allowed? Now you can see the waveform, that is the input waveform. Now in this input waveform, what are the frequencies present? The cosine is a signal actually. Cosine will have one frequency, cos will have a single frequency, single tone. Okay, in analog communication you would have gone through this term actually. Cosine is made up of single frequency. Now that single frequency is shifted up by, that is the DC bias is given. Okay, therefore this signal overall is having two components, that is the DC bias plus the frequency of the cosine. Now, after filtering, what is not there and what is remaining? What is remaining here? Constancy is remaining, correct? What is remaining? The DC is remaining, whereas variation, that variation is not there, correct?
Yes, sir.
So not there means what? It is removed, right?
Yeah.
Variation is suppressed or variation is removed or variation is filtered. By what factor? 100% removal, or you are multiplying by it by a 0. So where did we get this number from? This number is from our theory. So by what factor will this DC signal be removed or passed? The DC signal will be, the DC signal here is allowed or passed by a factor of 1. That is the multiplication factor. Okay.
Yes,
Whereas
sir.
the high frequency term will be allowed by by multiplication factor of so much. What is that amplitude here? 0. Therefore, high frequency term will be multiplied by 0. It is basically, if you are given this equation, we can guess the output like this. We can guess the output. Guess the output directly. Output is nothing but input. Whatever input is given, that only. That is cos omega 1n plus cos omega 2n. But there is a multiplication factor for this particular frequency. That multiplication factor is coming from the frequency magnitude response. That is the h of, okay, H1, multiplication factor H1, here multiplication factor H2. But what is H1 and H2? H1 is nothing but the magnitude response of h of e power j omega 1 magnitude, whereas H2 is obtained by considering the magnitude response h of e power j omega and its value at omega 2. Take its magnitude. Okay. So if you know the theory, from theory it is very easy to guess the output. Okay. So this we have analyzed for discrete time system. So if you understand for discrete time system, it is good enough. Any other questions? If you have any other questions, you can ask. Because theory you will be doing all such things. Say for example, you will be given some question like this, equation like this, you will be asked to find out something. But visualization and understanding will come only when you map your theoretical calculations with your laboratory, that is implementation. Only when you map this, all these things, it is from theory. You have to match your theory and your experiment. Then it will, I mean, one experiment if you can do properly, that is, I mean, almost many concepts you can understand across the subjects. So this particular topic is related to your DSP, analog communication, digital communication, and I mean even in linear integrated circuits also you'll get the frequency response. Electronic circuits you get this. So many places you get this. Any other questions? So if you don't have any other questions, I'll stop sharing the display. I'll mark the attendance. And I'll stop the recording also. So I suggest you complete your writing part of these laboratories. Unnecessarily, you don't wait until you are given a last date or something like that. Okay. Every 2 days after the lab, if you finish your writing part, okay, it will help you a lot. So this you can also, I mean, this is very much related to your theory. Okay. So it will help for your theory preparation also. So this kind of questions you'll get in GATE exam also. Okay. So if you have a good understanding of this, you can apply this understanding in your solving GATE problems also. Okay. So
Sir,
yeah, tell me.
sir, have you sent the lab manual, sir? Because I don't have it, sir. Lab
Lab
manual.
lab manual you want, right? That's what you are asking?
Yes, sir.
Okay. So lab manual, what I'll do is it is whatever is prepared for A section, that is your DSP course leader, I'll take it and share it. If you have already got it from them, that is what you can use it directly. Okay.
Can you send it, sir?
I'll share that. Okay. I'll share in your group.
Okay, sir. Thank you, sir.
Thank you. And also when I'm suggesting few things, if you try, for example, initially I told you in the last class we had discussed about autocorrelation. So and I suggested you to try to extract the pitch of your own voice. So if you try that, that is exactly how the projects will look like. Okay, the projects. So you will get a very hands-on experience. Okay, hands-on experience. You don't have to wait until your 7th sem and 8th sem to do your mini projects, or even 6th sem. You don't have to wait until your 6th sem. So these are the small experiments will give you good hands-on experience. Later, these concepts you can use in your bigger projects. Okay. So we can only suggest or advise, but we cannot enforce. So those who are interested, you can do. If you have doubts, you can come to me. So I can help you out. So I strongly encourage that kind of interaction. So otherwise, writing manual, all this nonsense, you have always you have been doing all this for the last 15, 16 years from your first standard. Now, what is expected from you is what is that you can do. So your ability to do is what is expected. Okay. So how much ever is there in your mind, if you cannot do and if you cannot demonstrate, that will not have much of a results. Okay. So if at all you want to professionally grow in this direction, this is what is the expectation. So with that, we'll stop today's discussion. If you have any questions, you can ask. Don't have, then I'm stopping the recording.